So we have this causal linkage that we've imposed. And between smoking and heart disease. And that has widened yet larger disparities that are exhibited by age, for example, between those 50 and up compared to younger in terms of the prevalence of heart disease. Or between those among different smoking status in terms of prevalence of heart disease. If there was no causal connection, we saw nonetheless, because of as someone ages, they have a higher chance of being an ever smoker, a higher chance of being of having developed heart disease. So an association there. It was not a causal association, but when we added this causal connection, it was larger. I'd like now, if we may, to look at some of the effects of positing effects of interventions here. So we're going to put in place a set of 3 interventions. They're going to focus on smoking initiation, smoking cessation, and smoking relapse. So with initiation, you want to prevent it. You want to lower the rate, the per year rate that someone develops smoking, starts smoking. If we have smoking cessation, we want to raise it, right? We want to raise the chance that someone can quit. For relapse, we want to lower that rate. We want to have less chance of having falling back into smoking. So we're going to put in place 3 scenarios for this. I noticed I wonder if we want to add stochasticity to current smoker hazard rates. Being smoking 1 cigarette per day might be different than 50. Could we add that to the specific action as a distribution? Yeah, so if you wanted to, if you believe that that was a priority for your model, and for the purpose of the model and even your stakeholders and so on, that's an important priority. There's a couple ways we could do it. One way would be to just say, well, there's this heterogeneity in the intensity of smoking. Some people are occasional smokers. We know that varies, for example, by ethnicity. There's more occasional smokers in certain cultures than there are in others. Occasional compared to continuous or committed. More sort of casual or social smokers compared to people using regularly. One way to do it would be, yes, it's state chart entry into Everstick. We could draw someone's closeted habits from a distribution. Generally, we'd want to put a little bit more thought into an intervention there, like something that might shift that intervention, for example. So we might want to have a certain multiplier that we could change for an intervention, or lower their or raise if we wanted to examine the effects of more smoking, some amount of packs per day that they smoke. And then we would need to be thinking about how does that impact heart disease risk, and potentially how does it affect the risk of ceasing if they're for some sustained time. If they're an occasional smoker, maybe they have a higher chance of quitting, being able to quit, and a lower chance because the lower physical dependence on nicotine of falling back. And so we'd want to think, what's the extent of that? Compellingly, what's such compelling understanding that even a parsimonious model, we want it to be able to express those dependencies. And that's what we would want to consider. But yes, we could do that, and that would actually be rather pleasing in some ways. Again, it's a matter of scope. Might want to ask, for example, the degree to which we want to characterize the fact that someone might begin as a occasional smoker, but then end up, depending through their social circle, we build our networks, and then they build us, perhaps smoking more and more, having a social support group that's predominantly smokers, and engaging in smoking related socializing that lead to more and more smoking. And we want to think about the scope of our model, if that's in the scope. But remember, models are tools for learning. They're not attempts to perfectly represent the world. So we want to have a scope that we're comfortable with, given our goals and given our scientific goals as part of that, often, or our policy related goals. And we want to think about that scope not as a static thing, but as what's the next priority? What can we build up? But yes, that's a rather pleasing idea. Okay. Fittingly, that was about thinking about. I tried to roll in something about interventions there, and I'm going to now, and I can't remember if I posted this, so I'm going to put up version 13 to the drive. Here we go. There, you can get that latest version. Okay. Time is ticking. Got about 25 minutes left for the afternoon. So what we're going to do here is we're going to put in place scenarios that posit a lower initiation risk, higher cessation risk, and lower relapse risk. So we're going to say, new, we're going to right click on the model, and we're going to say new experiment. We're going to say smoking cessation intervention. And we're going to put in place another one. We're going to say smoking. I'm sorry, I should have done this one first to be most natural. Initiation intervention. Maybe I'll copy and paste it. And the final one I'm going to put into place. Don't worry, I'll be setting the parameters. Just a minute. Smoking relapse intervention. And the goal here is to, again, lower the risk of initiation. The risk of initiation, the baseline, is 0.01 per year. So smoking initiation rate intervention, that scenario will lower that from its baseline. In fact, you can see its baseline here. It's not bold, so you know it's just baseline. We're going to change this from 0.01 to 0.05. Excuse me, what am I doing? Sorry, from 0.1 to 0.05. We lower the risk per year of them initiating smoking, them uptaking smoking. I think I'm actually going to lower that yet further. I'm going to lower it to 0.02. Okay. Smoking cessation. Do we want to raise that to help them or lower it to help them? Cessation. Oh, yeah. For cessation, do we want to raise it or lower it to help them kick their smoking habit? What do we want to do? Remember what the cessation rate is. It's the rate of going from current smoker to former smoker. Do we want that to be a higher thing to help them or a lower thing? Increase. Yeah, we want to help them in increase cessation. So from 4 per year, we'll raise it to 8. Okay. And for relapse, do we help them? You think about the effects of relapse. Will it help them if we raise it or if we lower it? We want less relapse. That's right. So instead of a rate of 6 times per year on average, or an average time before relapsing of 2 months, we will lower it to half of that, 3.0. And finally, just to emphasize this, I'm going to have one that combines 2. New experiment, new scenario. We're going to do smoking cessation and relapse intervention. There we go. And here, we're going to have a combined punch. Cessation will be 8.0. That was the intervene across measurement. Notice again, it makes it bold, indicating that it's been changed. And relapse will be 3.0, which is the value we used by lowering the relapse. Okay. 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 Very good. Very good. Okay. There we go. Okay, so let's check it out. Okay, first of all, make note of the baseline. I'm going to go run this for the baseline. We're going to compare to the baseline. And we're going to look at this unconditional one. Count with heart disease. Count with no heart disease. This is kind of the simplest one. I'm going to take a little screenshot of this, which I will squirrel away in some sort of document here. Here we go. Okay. There we go. Okay. Okay. Hey, come on. I don't know what's going on. It's being truculent. Okay. What's the matter with you? Okay. Try it again. That's really interesting. Why didn't it paste there? Okay. Now. Okay. Let's try it again. Paste. Okay, something funky is happening. Pardon me for a second. Let me just try putting it in here. It's not capture. Okay. Well, I don't want to belabor this. Let me just save it to a file. To my clipboard. Maybe there's something screwy with my clipboard going on. Okay, so baseline smoking heart disease. It's in my heart disease. Okay. Happiness. Okay, just put it in here. Yeah. Yeah. Hey, get over here. Yeah. There we go. This will memorialize it for our purpose. Stop that. Okay, now we're going to undertake an intervention. Let's focus first on the cessation, whether it's with nicotine patches or So transdermal patches, or there was a time where people are using e-cigarettes for this, or cognitive behavioral therapy, or other impacts for cessation. We're going to compare this with what we saw otherwise. And what we saw is here, the count with heart disease with the intervention is somewhere around 249, 250 here. In the other scenario, the baseline scenario up here, by contrast, wasn't all that much different. It was perhaps a similar range. It might have even been slightly lower because of stochastics. So there it didn't seem to really bend the curve much. Let's look at relapse intervention. So we might want to posit why that is, but I'd like to go through each of them first. So relapse intervention, where we lower the risk of relapse. Here we go. Well, if anything, this might be a little bit higher than with the smoking cessation. This is like 283, and it's possible that's due to stochastics, but we'll go back to the baseline. Let's see what the fraction is with heart disease in the baseline. I should have really measured it rather than just taking a picture of it. So here we go, or I could have copied it into a spreadsheet. Yeah. Okay, here it was, oh my goodness. No, excuse me. Here we go. 278 or so. Okay, so it doesn't seem to have been helped too much. Let's try both. Let's try the smoking initiation. Neither of those seem to really dramatically. Maybe one of them lowered it to 230, right? The number with heart disease. I think it was the cessation one. Smoking, oh, look at that. Okay. Count with heart disease, 345. Okay. So that's interesting. That was certainly not expected. I'm having trouble making sense of that, but we'll try to unpack this in just a minute. TAs start positing. Let's try smoking cessation and relapse together. Here it's 309, count with heart disease. What could there possibly be going on here? What could possibly be happening that here the count of people with heart disease is higher for both of those, for cessation and relapse together? Not quite a full court press, but pretty pronounced thing. For cessation and relapse jointly, kind of people with heart disease also quite high compared to baseline. Let's check it out. So I actually have a rather striking hypothesis about this. Not pre-planned, but here for the baseline, it's lower. 669, 273. Fewer people with heart disease. Have we done harm by our interventions? Have we done harm by preventing people from initiating? Have we done harm by preventing them from relapsing or encouraging them to cease? Have we actively done harm? Let's try an extreme. And that's one of the virtues of models. I'm striving to finish, not far off after our time. Let's create a new experiment. And let's say no initiation. No initiation. No starting of smoking. So what would I set the initiation rate to? What would I set it to if I wanted to turn off that effect, eliminate that causal pathway by which people go on to develop smoking? What would I set this to? What rate would mean that they don't transition?
0.
0. Let's do it. This is a lot of fun. Sleuth this down. Here we go. You notice by appearances, it's a lot fewer.
Good.
We have no. With heart disease, 401. What's going on? What's going on?
I'm so confused.
There's something we're not taking into account. What are we not taking into account? Exactly. Jeff hit it on the head. What we're not looking at here is the number that have died. And by preventing them from starting to smoke, we're encouraging people to have longer lives by also not having heart disease for longer. The longer they live, they're more likely to develop heart disease for other reasons, not through smoking. Maybe they're living longer lives. This is a reasonable question. So one way to examine about this is let's go look at the mean age in the population. Shall we not? Let's go look at the mean age in the population. I will start to clue us in. But another thing we could look at is we could actually look at how many have died cumulatively. And we could use that as the coup de grace for the final little bit here. So quickly, I'll look at the baseline. And we'll look at the mean age in the population. Maybe preventing people from smoking, we've shifted the mean age longer. Now, of course, it's going to impact risk of death for other reasons. So here, the mean age is 35.48, it says. And of course, don't take that incredibly seriously because in its exact value, because it depends on stochastics. Now let's try, so keep that in mind, 35.488. Now let's try no initiation. No initiation at all. There we go. 43.727. The mean age is higher. People are living longer. Living longer because we're preventing them from smoking. And that takes longer for them to develop heart disease. Okay, here we go. Let's do smoking and relapse, cessation and relapse together. 38.315. Yeah. So this will look pretty consistent. Pretty consistent. And the population size is much longer at the model end time, Jeff says. With the baseline, the population size by the model end, we'll run it. You can actually go look at this. It's 697 here that have lived, that are living at the end with no initiation. Here we go. So keep that in mind, 697 for the end time. Here it's 2,036 agents with no initiation. How do we enhance cessation and lower relapse? How many people remain in the population? There we go. 1,116. Folks, we're keeping people alive longer. And maybe some of those people we're keeping alive are now have become sons to have heart disease. After all, people who are not smokers have a chance of developing heart disease.
So if we looked at the fraction itself, it should not be that different. It should
The
be better.
fraction of,
Instead of looking at like I think we were looking at the count of actually people with heart disease. But if we looked at the compared to the population size, maybe it would be lower in the cessation, no?
maybe. Let's, because we have limited time, I agree, and we could readily do that. Because I want to show you something that cuts to the heart of the issue about deaths, I'd like to have a little bit of learning on the death side. So what I'm going to do is put in place a mechanism that'll keep track of cumulative deaths, if I may. And we're going to see if, for the baseline, the number of cumulative deaths is larger as we posit than it is for those interventions. So, how are we going to do that? Well, where do deaths take place in the model? They take place here. And when we come into this death state, we're going to increase a value that tallies up the number of deaths. So let's go up to main. And let's put in a variable here. Count deaths. Count cumulative deaths. Let's make very clear it's a count of cumulative death, the deaths till present. What type of variable is it going to be? If it's a count, it's a what? Is it a double? Is it a Boolean? Is it a color? It's a integer. It's going to start as 0 because 0 because nobody's died by the current time, by the start. And each time someone dies, we're going to increment this value. Count cumulative deaths. Okay, so we're going to go to population. We're going to go here to the deaths, and we're going to increment that. Yes, this is in main. The count cumulative deaths that we put it, because it's something that's shared across the population. Okay, here we go. You do main dot count cumulative deaths, and we're going to increase it by 1. There's other idiomatic ways to do this. You can do plus equals 1. You can do plus plus, but I'll just put it in the most bold way that someone might have encountered it in other programming languages like R or what have you. Cumulative deaths equals count cumulative deaths plus 1. My own preference would be plus plus or plus equals 1 because it communicates you're just increasing this thing. You don't have to look if it's the same on both sides. But this is certainly a widely recognized form. Okay, time is ticking. We have about 5 minutes left. I've just built this model. We are now going to run the baseline. We're going to see how many deaths have occurred to the final time. There we go. We're going to go to the model. Cumulative deaths is 4,612. Bear that in mind. 4,612. We know it's affected by stochastics a little bit. Now let's do no initiation. It's extreme. No one becomes a smoker. What's the count of cumulative deaths? 5,650. Did it go up or down? I'll remind you what it was for the baseline. There we go. I know it's late in the day, particularly for those on the Eastern. Here it's 5016. And with no initiation at all, 5,650. So actually here, more people have died. Okay, now I'm really confused. Okay, let's try these together. Let's cessation and relapse. Let's just make sure we understand. Okay. Here, 4,835. Okay, so there's going to be some variability. Let's use a random seed. I'm using it here. And this may be a little bit of our challenge using this particular one. Okay, a random seed. So each time it will be different. I'm going to run this a couple of times. And we'll keep track each time of it. So here we go. 5194. Okay. We're going to run it 5 times. 5194 here. We're going to run it again. We're going to see there's some variability. 5264. You know, I should really be putting these in a spreadsheet by all accounts so I can easily total them up. Office, here we go. LibreOffice Calc. Okay, so this is cessation and relapse. Okay, so 5192, 5194, 5264. 5264. Okay, I'm going to do it 3 more times here. Come on. Yes, you can do this in an automated way. I'm not putting this in place. The population size of the model end time is much larger. Okay, so here we have 5620. I'm going to actually copy it. And actually, you can copy it through this and paste it into your spreadsheet. I think Jeff is onto something. This is actually a very interesting matter of mutual interaction among things. Cumulative deaths can be higher for a case where we keep people around for longer. Why can it be higher when we keep them around for longer? Can anyone say? Because they have more kids. So the population gets larger and more kids can die eventually. Keeping people around longer can lead to more people in the population, which leads to cumulative number of deaths, which can be longer, larger. So here we're looking at a very coupled system, and I'm not sure actually if this current investigation is going to be as helpful as to sorting this out. And maybe that we have to do some sort of analysis per person year in the population or something along those lines. So this is going to be cessation and relapse. Now I'm going to do it with initiation. Here we go. And I know we're over. I recognize people may have to go. And I apologize for that. Okay. So smoking. So there's something called no initiation. Here it is. Okay. I'm going to run this 5 times. Yep. So there's some amounts of stochastics. This is 5650. Okay. One thing we could do is turn off bursts, disable new bursts in the model. That would be quite interesting. Oh, this should be a random number seed here. That first one will count as an independent one anyway, because from now on it's going to be independent. Here we go. count cumulative deaths. But I think as a matter of the larger population, I think that's a sign that people are living longer, engaging in birth and giving birth, and therefore there can be more deaths because of more births, and therefore deaths aren't necessarily going to be a definitive measure of success in reducing mortality because it's not a cohort we're looking at. We could make it a cohort if we disabled the births. And I think I'm going to press myself to do that after I do this little experimentation. Here we go. So this is kind of manual and awkward. I'm going to soon be showing you a way to do it automated, but we don't have time to set it up here. Here we go. One more for no initiation. There we go. Number of deaths, I've realized, though, is in association with the population size. Oops. Hey. Oh, man. Disabled it. Okay. Okay, so I think what I'm going to do is disable the number of bursts after I run the bursts after I've run the baseline. And what that's going to do is to basically mean we're examining a cohort and its effect through, and we're not going to be thrown off in terms of larger number of deaths from next generations. Man, it's not copying effectively. I'm not sure. My clipboard again seems to be bad. Jeff, what's your hypothesis? Is it the same as I'm talking about? Or do you have a different hypothesis? Wade said you've got it.
I have to apologize. I was working on a side project.
Okay. But Wade said you got it. So, like, do you have a hypothesis here?
He might be referring to a comment I had made at an earlier time in the experimentation.
Oh, okay. Okay. Yeah. So, sorry about that.
I
Okay.
can comment on what I thought Jeff was getting at.
Okay. Yeah.
When people live longer, and I
Yeah.
think you're approaching this with them having more children, and the total population is larger, than the total deaths will be larger.
Exactly. Yeah.
So by prolonging people's lives, by any means, we're actually increasing cumulative deaths.
Correctly. Correct.
It
That's
grows.
yeah, that's exactly my hypothesis here that I'm working off of. Okay, so sorry, this is a bit suspenseful, but I'm just doing my job figuring, doing this one, recording deaths. So we have a data set there before I change the model, and I'm close enough to being done here. Oh, okay. I think I'll leave that. I'm gonna in I'll come back to that. But first, I want to turn off birth rate. How would I turn off birth rate? How would I disable births? Anyone? So I'll show you a nice little trick. I'm going to copy baseline, and I'm going to make it baseline. So I'm going to make it no births. So it's baseline with no births. How would I turn off births? Can anyone look at this and have a thought about how to turn off births?
Just birth rate 0.
Birth rate is 0. Hey! Oh, man. Sorry, folks. My anti-logic died just at the time we needed it. Okay.
He's
Okay.
ready to give up.
It's like it's on the cusp of greatness and it died. Okay. Cusp of insight. Drawn out of our hands. Okay. So thankfully, my motto that my students know is also save early, save often. So we have this here model, and what we don't have is this no bursts. So I'm going to copy that. Hey, come on. Yes. Copy, paste. So I'm copying baseline, and I'll call it no bursts. No, hey, no bursts. Yeah. Okay. And we're going to set the birth rate to 0. This is just going to be a cohort going through. No, what the heck? No issues of new births in bigger population, and therefore more deaths possible. No births. And then we're going to have no initiation also with no births. So we're going to have a version of that that's just a cohort. Maybe instead of saying no births, I'm going to say cohort, no births, or no births cohort. I'm just going to say it that way. And for no initiation, I'm going to say no initiation, no births cohort. There we
I
go.
have a actually related to births. In our assumption on a birth event, it does not depend on the people there is actually like in the model.
It doesn't depend on, sorry?
So the birth rate basically does not really depend on how many people are. So it's not actually people that are giving birth. We're just adding a new person, right?
No, it actually is. And I'll explain that in just a second. So I've just added 3 experiments. Sorry, no birth cohort. So I added 3 experiments. They're variants of the baseline, that one is called no birth cohort. No initiation, it's no initiation, no births, and I have to change this to 0. And then smoking cessation and relapse, no birth cohort. Okay, so to answer Sarah's question, here this birth event occurs from within a person, so that person has to be alive for them to be eligible. Once they're removed from the population, they're not going to give birth. So this is occurring actually on a per person basis, that there's this certain birth rate that applies for each and every person that's still alive, and if they die, they're gone from the population. So if the population is larger, a larger number will experience this birth event. If the population is smaller, a smaller number will experience the birth event in a given year. So it actually is, yeah. Okay. So now that we've reached the moment of truth, we have this hypothesis. We have this perplexing observations, did we not? That we didn't seem to lower the prevalence of heart disease in a material way. And it varied a little bit by stochastic, but big picture, we didn't seem to have a big impact. But more than that, we didn't seem to lower the number of deaths. In fact, it seemed there was a case to be made, maybe the number of deaths was higher. And we were scratching our heads. And the question is, of course, is this a bug? Is it a defect with design defect with the model? Is it an implementation defect, something silly we did? We meant to do X, we did Y instead, or is it a design defect or some flaw in our thinking? But I was honing in, and Jeff was honing in this idea that, look, it's a complicated thing with deaths, because deaths come from a population. And if we're successful in having people live longer, we won't be increasing the number of their deaths, but we will be increasing the chance they give birth and the number of babies to which they give birth over their lifetime, which could lead to more deaths in the next generation and subsequent generations. So actually saving people can lead to more deaths as a death statistic. This is my hypothesis, but it hasn't been borne out yet. It hasn't been shown yet. So what did I do to test this hypothesis? This is very much part of the art of modeling. And it's part of the utility of modeling that we can do this. We can turn off effects like we turned off death before, right? To test a hypothesis. We can turn off initiation and see how that affects things to test our thinking about why we're seeing certain effects. Here we've turned off births. So we're dealing with a cohort, right? There's a cohort there, and we follow them as they age. There's still deaths. There's no births. And we're going to look here at the number of deaths that have occurred cumulatively. And that is going to be a marker of how many people we've saved. We will also look at the prevalence of heart disease. So without trying to do it on a per realization basis that it's going to require me to run it many times, let's dive into this. So no burst. So we're going to do a no burst cohort. Maybe I'll call this baseline no burst cohort just to make it extremely obvious. I'm going to call this version 15, and I will post it forthwith. Okay, here we go. Baseline no burst cohort. Okay, the population goes down. Yeah, we know about that. Why is the population dropping precipitously? Have we killed off everyone? No. No, it's because there are no births coming in. Count of cumulative deaths, 998. Everyone except 2 people in the baseline, 998. Everyone except 2 people. Look at them. Okay. 2 people left. Yeah, wait, I'm just about done here, so I'm going to finish it. We'll talk about this more in the morning. Okay, how about a situation where smoking cessation and relapse focused intervention? Here we go. Here we go. Here we go. Well, 2 people too. 998. Okay. How about a no initiation intervention with no burst cohort? It's a little bit hard because we're having few people survive. 995. We have 5 instead of 2. Okay. Yeah. We could have each of those run for a somewhat shorter time just to have a bigger statistical sample. I think I'll have each of those run for 100 years. Not 200. Okay. And no initiation, run it for 100 years. There we go. And finally, smoking cessation and relapse, 100 years. That will give us a bigger, more statistically significant sample to test this with. Right now it's a bit anecdotal with 2 versus 5. Here we go. So this is the baseline no burst cohort. 946 people have died. 946. Let's check out the fraction without heart disease here. Okay. Excuse me. Do we have a prevalence of, do we have something about prevalence of heart disease? 0.63 in the population for the current people living. 946 have died, all but 54. Okay, that's a variant of the baseline. Okay, are you gripping your seat? Here we go. No initiation, no burst cohort. How many died with that? So this is baseline, 946 and 0.63 prevalent. No initiation. No initiation. We have left 935. Oh, sorry. Excuse me. Number of deaths that occurred, 935, 946, 935. We've reduced the number of deaths. And what, pray tell, is the prevalence of heart disease amongst that surviving population? 0.446, down from 0.63 in the baseline. We have helped that population, that cohort. And finally, cessation and relapse intervention, no birth cohort. We run it. We examine the count of deaths. No cessation or relapse. How many have cumulatively died? 901. 901. That's interesting. And what is the population prevalence of smoking? Of heart disease? 0.485. So there, it's actually higher in population prevalence of heart disease than in the uptake, initiation. But fewer people have actually died. And we could run it several times to assess whether that's statistically significant. But the picture seems to be emerging that both of those have considerably lower fractional prevalence of heart disease, from 0.63 down to 0.446 and 0.485. And lower number of cumulative deaths, from 0.946 to 935 and 901. And I would strongly suggest that if we were to run that again with the no burst cohort, we would again see something lower. And we could run it many times. We could run it 5 times, for example, to get some statistical sample. This time it's again 922, yet lower in terms of cumulative deaths and in terms of population prevalence of heart disease, lower again than the baseline, 0.359. So it appears that our hypothesis has been borne out, or at least not falsified. What we are seeing is consistent with our hypothesis. The hypothesis that these counterintuitive results, remember, nonlinear systems, complex systems can give rise to counterintuitive results. How is it, we stressed, how is it possible that by interventions to help someone's cessation and relapse situation, but help someone's smoking status among those who are ever smokers by increasing cessation and lower relapse, how is it we could have caused more deaths? How is it we could have raised the prevalence of smoking by the end? Of heart disease by the end. We now have a clear answer. Keeping people alive longer. They can develop heart disease by other means, but perhaps most importantly, by keeping them alive longer, they can give birth for the next generation. And the size of the population is much larger, as Jeff noted. Probably should have recorded that. And therefore, there can be more deaths for each of those interventions. So this idea that we did harm, that we had more deaths caused by those interventions, is not a sign. The fact that we have more deaths was not a sign that we failed the population. It wasn't a sign that we came up short with our intervention. It was not a sign that we have inflicted grievous harm. It's a reflection of the fact we kept people alive more. We led to more flourishing in the next generation and cumulatively over deaths. And we see that in the total population size. But we see it if we turn off births increasingly clearly here, that in fact our interventions in that cohort in which we intervene, first, lower deaths, lower prevalence of heart disease. This can be a signal or reminder, a sterling example of how we can easily be perplexed by the results of a complex system, easily thrown off. But where models, by allowing us to turn on and off certain pathways, by allowing us to sharpen our thinking by examining certain effects separate from others, can provide us a sharpened thinking about the system, a sharpened thinking about the effects of here keeping people alive decades longer. And the reliability under certain contexts of open populations of using measures like fractional prevalence of heart disease to assess benefit, or cumulative deaths to assess benefit. So with those words, I will stop today's session and we'll resume fresh and with a less sore throat on my side at 8:30 tomorrow morning. Thank you, everyone. Thank you for your patience, and thank you for the extra time you spent. It's been an honor. So take care there. And I'd like to chat with the TAs for a brief time. Thanks so much.